In this video, we're going to be discussing the different types of solids that exist as well as some of their properties. You are going to need something to write with, you are going to need a notebook, and once you have those things ready, let's go. Okay, so there are 5 different types of solids we're going to work with, and we can break them down to 2 general classifications. The first classification is what's called a crystalline solid. What makes a crystalline solid crystalline is that it has regularly repeating units that you call a lattice. Sometimes the lattice shape will be like a cube. Sometimes the lattice shape will be a hexagon. Sometimes the lattice shape will be what we call rhombic. We're not really going to get into the different shapes of crystalline solids. We're going to work more with what's at each of those individual, what we call lattice points or corners of the crystal. Now, any solid that's not crystalline, so it doesn't have these regularly repeating units, is what we call an amorphous solid. Glass, as an example, is an amorphous solid. There is no set crystalline structure to glass. It just exists as a random collection of different silicon and oxygen atoms dispersed about in no real pattern. Right? So amorphous is one of our 5 classifications. The other 4 that we're going to go over are all different types of crystalline solid. Right? And again, the only thing that's different about these solids is what makes up each of these individual corners or lattice points. The first type of crystalline solid we're going to go over is the one you're probably most familiar with, and that is the ionic solid. In an ionic solid, the lattice points, so the corners of those crystals, are the individual positive and negative ions. So the image that I have here is a sodium chloride or table salt crystal. What you can see is you have chloride ions, then sodium ions, then chloride ions, then sodium ions, repeating in a pattern based on the charges of the ions involved. Right? So alternating positive and negative charges forms this relatively stable crystalline structure. And what's holding these different lattice points together are the ionic bonds between the positive ion and the negative ion. Now, because ionic bonds tend to be very strong, ionic properties have a few specific, or ionic solids, have a few specific properties. So, first thing is they tend to have very high melting points. Table salt, for example, has a melting point of about 750 degrees Celsius, right? And that's just a +1, -1. Once you start getting into things like magnesium oxide, where you're working with +2 and -2, melting point can be 1,500 degrees C. In their solid state, ionic solids do not conduct electricity. The reason why is that in order to conduct electricity, the charge needs to be able to flow. There's no flow in a solid, but if we melt it into a liquid, or if we dissolve the ionic compound in water, that will allow those charges to move about, and then those will conduct electricity though. So ionic solids, non-conductive as a solid, but conductive as a liquid or in aqueous solution. And again, this also brings up the idea that some ionic compounds do dissolve in water. A lot of them do actually. Right? What it depends on is it depends on the sizes and charges of the ions involved to see whether or not it's more favorable for the substance to be held together as a crystal energetically or break up and have intermolecular forces, attractions with the water molecules. When we get into equilibrium, one of the things we're going to learn is that theoretically every ionic solid is soluble. It is only a matter of how much it will dissolve. Some things may only dissolve on the orders of micromolar. Okay, so these are ionic solids. Our second type of solid is what we call a network covalent solid. You also see these referred to as network solids. They're like ionic solids in that the lattice points, in this case, instead of being ions, are individual atoms. Right, so the 3 that I have over there are graphite, diamond, and silicon. In graphite and diamond, what's holding that solid together is the carbon-carbon covalent bonds. Right? The difference between graphite and diamond, though, is that graphite is a network covalent solid in 3 dimensions. Right? You have your tetrahedral carbon atoms pointing up, down, left, right. But in graphite, it's only a 2-dimensional arrangement. So you have layers of graphite that form one on another. That, for example, is the reason why graphite's used as a lubricant and why it's also used in pencils. right? The fact is you can write with it and it will only take off one layer of graphite at a time. And by the way, one layer of graphite is what we call graphene. Okay, so they are held together by covalent bonds. Now, because again, covalent bonds are extremely strong, that means it's going to be hard to pull them apart. So network covalent solids, extremely high melting points. We're talking on the order of 2,500 to 3,000 C if they melt at all. Some of them are actually just likely to go directly from solid to gas and not even become a liquid. Network covalent solids do not at all dissolve in water. And as far as conductivity goes, some of them, like for example graphite and silicon, can conduct a little bit in the solid state. They're what are called semiconductors, but most network covalent solids generally don't conduct in the solid state. So if it's a semiconductor, it's probably network covalent, but not every network covalent will conduct electricity as a solid. And again, you don't have to worry about them dissolving in water, so there's no aqueous conductivity for these either. Our third type of solid is what we call a molecular solid. So in an ionic solid, the lattice points are individual ions held together by an ionic bond. In a network covalent solid, they were atoms being held together by covalent bonds. For a molecular solid, the lattice points are entire molecules. And what's holding these molecules together, you might ask? Well, intermolecular forces, right? Molecular solids are held together by dispersion, dipole-dipole, and hydrogen bonding, whatever the individual molecule might have. Now, because these intermolecular forces are much weaker than a covalent or ionic bond, that gives them lower melting points, right? Water, for example, melts at 0 degrees Celsius. Sugar, which is also a covalent compound, will melt at around a couple of 100 degrees Celsius. So, a lot lower melting point than that of even table salt. Now, as far as solubility in water, again, we have to keep in mind like dissolves like. The only substances that will dissolve in water are the substances that are polar. The more polar the substance is, the more it will dissolve in water. The less polar it is, the less it will dissolve in water. And then our last type of solid is what we call a metallic solid. These work completely differently than any type of solid we discussed so far. The reason why is that in a metallic solid, what happens is all of its valence electrons basically become this delocalized sea where they can go back and forth as they choose in whatever direction they want. So you have positive ions like life rafts floating in a sea of electrons. Now that gives us some unique properties, right? Metallic solids, most of them have relatively high melting points. There are always a couple of exceptions, for example, like mercury, which is a liquid at room temperature. Metallic substances will always conduct in the solid state and in the liquid state, right? So if I had copper, solid copper conducts. It's the reason why we use it in electrical wiring. If I melt the solid copper and turn it into liquid, it will also conduct. And metallic solids are not water soluble. They don't have similar intermolecular forces than water does, so they will not dissolve. So those are the 5 basic types of solid and some of their properties. What you're going to need to be able to do with this is I'll give you a list of properties of a substance, and I'll ask you to tell me what type of bonding it has or what type of solid it is. You'll need to be able to compare and do that. In our next video, which is the last one for this chapter, we'll start talking about solutions of solids, otherwise known as alloys.